Magnetic fields. 6.3. State that moving charges give rise to magnetic fields. We know that when you have a current, you can get an electromagnet from the current. If you wrap the wire around an iron nail, for example, you can make that nail turn into an electromagnet. The Örsted Demo. This is an example of one of the most epic failures in the history of science. There was an argument between Örsted, who was a Danish physicist 150 years ago, and a British scientist called Maxwell. And Maxwell insisted that magnetic fields and electric fields had a lot to do with each other. They were basically connected in some way. They were basically two facets of the same force. Örsted insisted that electric fields and magnetic fields had nothing to do with each other. If you had an electric field, you had an electric field, or if you had current, it had nothing to do with magnetism. And to prove this in front of a lecture hall of 200 students, he said, I will show you that there is no magnetic effect when you turn on the electric current. And this is what happened. And of course, what happened, he turned on the current, and all these compasses that were placed nearby started twitching because they were affected by the current. It was a real epic fail on his part anyway. But it's remembered as the proof that electricity and magnetism are tied together. And this is basically what happens. If we have a current going through a board like this, you find that the magnets would line up in this direction. If the current goes the other way, the magnets goes in the other direction. They don't point towards the wire or away from the wire, they point around the wire. So how can this be explained? Well, it's quite simple really. When we have a current, we will have a magnetic field lines acting around the wire. So this is basically what happens. A current goes this way, there's the current going this way, the magnetic field lines will go around it in concentric circles. They don't overlap, they don't touch, they just have the same center. There we go. And what should happen is these lines should get further apart as they move away from the current, and that shows that the magnetic field strength weakens as you go away from the current. And here's another example. This is not a good example because this shows that the field strength is not changing, but of course it does. Now we have Maxwell's corkscrew rule to basically decide which way the magnetic field line is going. Now if we have the current coming this way, remember the current is a flow of positive charges, the magnetic field lines will go in an anti-clockwise direction. How can we remember this? Well, if you think of the motion, the direction of a corkscrew, the rotation of the handle will be in the same direction that the magnetic field lines will go. And this is another way of looking at it. If your thumb shows the direction of the current, the direction that your fingers wrap around your hand shows the direction of the magnetic field. Now here's an interesting example. We have this cross means that the electric current is going away from us. This dot means the current is coming towards us. This cross, which means the current is going away from us, using the right grip rule, or using Maxwell's corkscrew rule, we can see that the current is going away from us, the magnetic field lines will go in a clockwise direction. When the current comes towards us, the magnetic field lines will go in an anti-clockwise direction. When you have a loop of wire like this is basically a loop of wire. The loop is coming out of the screen and then back into the screen, behind, out, and then in, and so on. Then you're going to get a magnetic field here. This will basically be like the north side, this will be the south side of this electromagnet. Now the Maxwell demo. He was able to show that if you had a permanent magnet and you have a magnetic field caused by a current, what's going to happen? Well, they're going to interact. There's going to be some force and there will be some motion. And this is basically it. If the magnetic field lines are going downwards and we have a current carrier at 90 degrees to this, then this current carrier will be forced to the right. So basically they're all at 90 degrees. This is vertically, this is coming out of the board, and this is moving to the right. And this is basically that can be described with Fleming's left-hand motor rule, which is this: if the first finger is a field, the second finger is the current, the thumb would show the motion. So if you have the first finger going down and you have the current coming towards you, it must mean that the motion, the force of the wire, will be in this direction. Now, how can we look at that in a bit more detail? What is happening to the fields in this case? We have two fields. One is caused by the current carrier, one is a permanent magnet. When you add these two fields, there will be forces between them. So what we're going to do is look at this field. So this is the current carrying wire causing this magnetic field. When you add it to the magnetic field, what we end up with is these lines are going from left to right, these are going from left to right, so they're all in the same direction. But underneath, the lines here are going from right to left, these are going from left to right, so they basically cancel out at some point. So they cancel out at this point. Now this causes what's called a neutral point, and the wire will be forced down towards the neutral point, which will keep on moving down, so the wire will be continually forced downwards. This is called a catapult field. And here's another example. This is going from left to right. These lines here will cancel out, and the current carrier will be forced upwards. If we have two current carriers, this is a loop. The current is coming out here and is going in there, so it keeps on going out, in. If we take this one will be forced upwards using Fleming's left-hand motor rule. This one will be forced downwards using Fleming's left-hand motor rule. So this thing will tip up and down. And this is a picture of the fields when you added them together. This is how we use this principle to show how a motor works. We have a coil of wire like this, where the current is going one way and the current is going the other way. This one way will be flipped down, this will be flipped up, and therefore this will spin round. Then what happens is it goes over to the other side, and then this breaks this contact, and then this side, the side that was on number one here, which ends up over here, this will then be pushed down, so it will start to rotate in a anti-clockwise direction. This is made much smoother by having many loops of circuit. This is one loop of circuit, this is another loop, this is another loop, so this ends up moving in a much smoother way. Determine the direction of the force on a charge moving in a magnetic field. For example, a magnetic field goes into the board, the proton moves from left to right, which means the current goes from left to right. So which way will the proton go? It will go upwards. Now, two parallel current carrying wires. We have similar currents. This is going away from us, this is also going away from us. Now each one will generate its own magnetic field. This is the magnetic field due to this one, and this will interact with the magnetic field due to this one. Now this magnetic field is going in an anti-clockwise direction, so what's going to happen here is that this field here is going to cancel out. You will get a neutral point here, so each wire will be drawn towards this neutral point, in other words to each other. Force will be equal because this is a Newton's third law pair, but they will be forced towards the middle, so there will be force of attraction. We have like currents actually attract, and this is a sketch of what it looks like if it's opposite currents. There's a very compact magnetic field between them, and that will push them apart. So unlike currents repel. Now this leads us on to the definition of the ampere. Now if we have two infinitely long parallel wires, this one and this one, which are 1 meter apart, and each one carries 1 amp of current, there will be a force of attraction between them for each meter of the wire of 2 times 10 to the negative 7 newtons. And this defines what 1 ampere is. So it's that current that when you have two infinitely long parallel wires 1 meter apart, it provides a force of 2 times 10 to the minus 7 newtons for each meter. Okay, what does this force depend on? It depends on the size of the current, it depends on the strength of the magnetic field, but it also depends on the length of the wire and the angle that they meet. Since we're talking about 90 degrees, we're talking about the sine of an angle. Now if the angle is less than 90 degrees, then we have to take the sine of that angle, which is going to be less than 1. Determine the magnitude and direction of a magnetic field. There are two equations that we need to know. F is equal to Bill sine theta, which is what we basically looked at, and F is equal to BQV. So these two equations you need to know. F is equal to Bill sine theta. B is the magnetic field strength. I is the current. L is the length of wire which is in the magnetic field, and the theta is the angle between the magnetic field lines and the wire. If they're not at 90 degrees, then the force is reduced. If they're actually parallel, then sine theta will be equal to 0 and there will be no force acting on the wire. The second equation is to look at F is equal to BQV. If you have a charge which is moving at a velocity v, the charge is q in a magnetic field strength b, it will be forced to move in a circle. And this force, which will provide a force which makes it go in a circle, which will be a centripetal force, will be equal to BQV. B is the magnetic field strength, Q is the charge on the particle, V is the velocity of the charged particle. It has to be moving. If the velocity is 0, if the particle is not moving, there will be no force on the charged particle in a magnetic field. So this is the equation we use. F is equal to BQV. B is the magnetic field strength, Q is the charge on the particle, V is the velocity of the charged particle. So we have a potential difference of 400 volts. It passes from left to right, and the radius of curvature is 1 meter. So how do we do that? We need these facts. M is the mass of the electron, E is the charge on an electron. So the first step, find the V of the electron, find the velocity of the electron, if you know the accelerating voltage. 2. Find the force needed to make it move in a circle, which is the centripetal force. C. Rearrange B's F is equal to BQV to find the B. Try to do that now. The hints are as follows. Now, step 1. You may know that the kinetic energy is equal to the voltage times by the charge. If you haven't studied electricity topic yet, then you won't know this, so I'm telling you this for free. So the kinetic energy is 1.6 times 10 to the minus 19, because it's a charge on an electron, times by the volts. This gives the kinetic energy of the electron. Then we have to use a half mv squared to find V. Once you know V, you know the mass, you know R, you can work out what the centripetal force will be. Stage 3, once you know F, you know Q, it's a charge on the electron, you know V, you can work out what the magnetic field strength is. So try to do that now.